Max Karl Ernst Ludwig Planck, FRS, was a German theoretical physicist who originated quantum theory, which won him the Nobel Prize in Physics in 1918. Planck made many contributions to theoretical physics, but his fame rests primarily on his role as originator of the quantum theory. This theory revolutionized human understanding of atomic and subatomic processes, just as Albert Einstein unregistered trademark S theory of relativity revolutionized the understanding of space and time. Together they constitute the fundamental theories of 20th-century physics. Early life and career: Planck came from a traditional, intellectual family. His paternal great-grandfather and grandfather were both theology professors in Gar-Paragraftingen. His father was a law professor in Kiel and Munich. Planck was born in Kiel, Holstein, to Johann Julius Wilhelm Planck and his second wife, Emma Porzig. He was baptized with the name of Karl Ernst Ludwig Max Planck. Of his given names, Marx was indicated as the primary name. However, by the age of 10 he signed with the name Max and used this for the rest of his life. He was the sixth child in the family, though two of his siblings were from his father's first marriage. Among his earliest memories was the marching of Prussian and Austrian troops into Kiel during the Second Schleswig War in 1864. In 1867 the family moved to Munich, and Planck enrolled in the Maximilians Gymnasium School, where he came under the tutelage of Hermann Marwan-Kortelaer, a mathematician who took an interest in the youth, and taught him astronomy and mechanics as well as mathematics. It was from Marwan-Kortelaer that Planck first learned the principle of conservation of energy. Planck graduated early, at age 17. This is how Planck first came in contact with the field of physics. Planck was gifted when it came to music. He took singing lessons and played piano, organ and cello, and composed songs and operas. However, instead of music he chose to study physics. The Munich physics professor Philipp von Jolly advised Planck against going into physics, saying, "In this field, almost everything is already discovered, and all that remains is to fill a few holes." Planck replied that he did not wish to discover new things, but only to understand the known fundamentals of the field, and so began his studies in 1874 at the University of Munich. Under Jolly's supervision, Planck performed the only experiments of his scientific career, studying the diffusion of hydrogen through heated platinum, but transferred to theoretical physics. In 1877 he went to Berlin for a year of study with physicists Hermann von Helmholtz and Gustav Kirchhoff and mathematician Carl Weierstrass. He wrote that Helmholtz was never quite prepared, spoke slowly, miscalculated endlessly, and bored his listeners, while Kirchhoff spoke in carefully prepared lectures which were dry and monotonous. He soon became close friends with Helmholtz. While there he undertook a program of mostly self-study of Clausius's writings, which led him to choose heat theory as his field. In October 1878 Planck passed his qualifying exams and in February 1879 defended his dissertation, Arbeiten Hauptsätze der mechanischen Wahrscheinlichkeitstheorie. He briefly taught mathematics and physics at his former school in Munich. In June 1880, he presented his habilitation thesis, Gleichgewichtszuständigkeit der isotroper K-Paragraphe per investierenden Temperaturen. Academic career: with the completion of his habilitation thesis, Planck became an unpaid private lecturer in Munich, waiting until he was offered an academic position. Although he was initially ignored by the academic community, he furthered his work on the field of heat theory and discovered one after another the same thermodynamical formalism as Gibbs without realizing it. Clausius's ideas on entropy occupied a central role in his work. In April 1885 the University of Kiel appointed Planck as Associate Professor of Theoretical Physics. Further work on entropy and its treatment, especially as applied in physical chemistry, followed. He published his treatise on thermodynamics in 1897. He proposed a thermodynamic basis for Svante-Arrhenius's theory of electrolytic dissociation. Within 4 years he was named the successor to Kirchhoff's position at the University of Berlin presumably thanks to Helmholtz's intercession and by 1892 became a full professor. In 1907 Planck was offered Boltzmann's position in Vienna, but turned it down to stay in Berlin. During 1909, as University of Berlin professor, he was invited to become the Ernest Kempton Adams Lecturer in Theoretical Physics at Columbia University in New York City. A series of his lectures were translated and co-published by Columbia University professor A.P. Wills. He retired from Berlin on January 10, 1926, and was succeeded by Erwin Schröer. Family. In March 1887 Planck married Marie Merck, sister of a schoolfellow, and moved with her into a sublet apartment in Kiel. They had 4 children, Karl, the twins Emma and Greet, and Erwin. After the apartment in Berlin, the Planck family lived in a villa in Berlin-Grunewald, Wagenheimstrasse 21. Several other professors of Berlin University lived nearby, among them theologian Adolf von Harnack, who became a close friend of Planck. Soon the Planck home became a social and cultural center. Numerous well-known scientists, such as Albert Einstein, Otto Hahn and Lise Meitner were frequent visitors. The tradition of jointly performing music had already been established in the home of Helmholtz. After several happy years, in July 1909 Marie Planck died, possibly from tuberculosis. In March 1911 Planck married his second wife, Marga von Hoesselin. In December his 5th child Hermann was born. During the First World War Planck's second son Erwin was taken prisoner by the French in 1914, while his oldest son Karl was killed in action at Verdun. Greet died in 1917 while giving birth to her first child. Her sister died the same way 2 years later, after having married Greet's widower. Both granddaughters survived and were named after their mothers. Planck endured these losses stoically. In January 1945, Erwin, to whom he had been particularly close, was sentenced to death by the Nazi Volksgerichtshof because of his participation in the failed attempt to assassinate Hitler in July 1944. Erwin was executed on January 23, 1945. Wives, Marie Merck, Marga von Hoesselin, children, Karl, twins Emma and Greet, Erwin, Hermann, professor at Berlin University. In Berlin, Planck joined the local physical society. He later wrote about this time, "In those days I was essentially the only theoretical physicist there, whence things were not so easy for me, because I started mentioning entropy, but this was not quite fashionable, since it was regarded as a mathematical spook." Thanks to his initiative, the various local physical societies of Germany merged in 1898 to form the German Physical Society. From 1905 to 1909 Planck was the president. Planck started a 6-semester course of lectures on theoretical physics, dry, somewhat impersonal according to Lise Meitner, using no notes, never making mistakes, never faltering. The best lecturer I ever heard according to an English participant, James R. Partington, who continues, there were always many standing around the room. As the lecture room was well heated and rather close, some of the listeners would from time to time drop to the floor, but this did not disturb the lecture. Planck did not establish an actual school. The number of his graduate students was only about 20, among them, 1897 Max Abraham, 1904 Moritz Schlick, 1906 Wolfram Eisner, 1906 Max von Laue, 1907 Fritz Reisch, 1912 Walter Schottky, 1914 Walther Buff. Black body radiation. In 1894 Planck turned his attention to the problem of black body radiation. He had been commissioned by electric companies to create maximum light from light bulbs with minimum energy. The problem had been stated by Kirchhoff in 1859, how does the intensity of the electromagnetic radiation emitted by a black body depend on the frequency of the radiation and the temperature of the body? The question had been explored experimentally, but no theoretical treatment agreed with experimental values. Wilhelm Wien proposed Wien's law, which correctly predicted the behavior at high frequencies, but failed at low frequencies. The Rayleigh-Eurogen's law, another approach to the problem, created what was later known as the ultraviolet catastrophe, but contrary to many textbooks this was not a motivation for Planck. Planck's first proposed solution to the problem in 1899 followed from what Planck called the principle of elementary disorder, which allowed him to derive Wien's law from a number of assumptions about the entropy of an ideal oscillator, creating what was referred to as the Wiener-Planck law. Soon it was found that experimental evidence did not confirm the new law at all, to Planck's frustration. Planck revised his approach, deriving the first version of the famous Planck black-body radiation law, which described the experimentally observed black-body spectrum well. It was first proposed in a meeting of the DPG on October 19, 1900 and published in 1901. This first derivation did not include energy quantization, and did not use statistical mechanics, to which he held an aversion. In November 1900, Planck revised this first approach, relying on Boltzmann's statistical interpretation of the second law of thermodynamics as a way of gaining a more fundamental understanding of the principles behind his radiation law. As Planck was deeply suspicious of the philosophical and physical implications of such an interpretation of Boltzmann's approach, his recourse to them was, as he later put it, an act of despair. I was ready to sacrifice any of my previous convictions about physics. The central assumption behind his new derivation, presented to the DPG on December 14, 1900, was the supposition, now known as the Planck postulate, that electromagnetic energy could be emitted only in quantized form. In other words, the energy could only be a multiple of an elementary unit, whereas Planck's constant, also known as Planck's action quantum, and is the frequency of the radiation. Note that the elementary units of energy discussed here are represented by and not simply by. Physicists now call these quanta photons, and a photon of frequency will have its own specific and unique energy. The total energy at that frequency is then equal to multiplied by the number of photons at that frequency. At first Planck considered that quantization was only a purely formal assumption. Actually, I did not think much about it. Nowadays this assumption, incompatible with classical physics, is regarded as the birth of quantum physics and the greatest intellectual accomplishment of Planck's career. The discovery of Planck's constant enabled him to define a new universal set of physical units, all based on fundamental physical constants upon which much of quantum theory is based. In recognition of Planck's fundamental contribution to a new branch of physics, he was awarded the Nobel Prize in Physics in 1918. Subsequently, Planck tried to grasp the meaning of energy quanta, but to no avail. My unavailing attempts to somehow reintegrate the action quantum into classical theory extended over several years and caused me much trouble. Even several years later, other physicists like Rayleigh, Jeans, and Lorentz set Planck's constant to zero in order to align with classical physics, but Planck knew well that this constant had a precise non-zero value. I am unable to understand Jeans' stubbornness. He is an example of a theoretician as should never be existing, the same as Hegel was for philosophy. So much the worse for the facts if they don't fit. Max Planck wrote about Planck, he was, by nature, a conservative mind. He had nothing of the revolutionary and was thoroughly skeptical about speculations. Yet his belief in the compelling force of logical reasoning from facts was so strong that he did not flinch from announcing the most revolutionary idea which ever has shaken physics. Einstein and the theory of relativity. In 1905, the three epochal papers of the hitherto completely unknown Albert Einstein were published in the journal Annalen der Physik. Planck was among the few who immediately recognized the significance of the special theory of relativity. Thanks to his influence, this theory was soon widely accepted in Germany. Planck also contributed considerably to extend the special theory of relativity. For example, he recast the theory in terms of classical action. Einstein's hypothesis of light quanta, based on Philipp Lenard's 1902 discovery of the photoelectric effect, was initially rejected by Planck. He was unwilling to discard completely Maxwell's theory of electrodynamics. The theory of light would be thrown back not by decades, but by centuries, into the age when Christian Huygens dared to fight against the mighty emission theory of Isaac Newton. In 1910, Einstein pointed out the anomalous behavior of specific heat at low temperatures as another example of a phenomenon which defies explanation by classical physics. Planck and Nernst, seeking to clarify the increasing number of contradictions, organized the first Solvay conference. At this meeting Einstein was able to convince Planck. Meanwhile, Planck had been appointed Dean of Berlin University, whereby it was possible for him to call Einstein to Berlin and establish a new professorship for him. Soon the two scientists became close friends and met frequently to play music together. World War I. At the onset of the First World War, Planck endorsed the general excitement of the public, writing that, "Besides much that is horrible, there is also much that is unexpectedly great and beautiful, the smooth solution of the most difficult domestic political problems by the unification of all parties. The extolling of everything good and noble." Nonetheless, Planck refrained from the extremes of nationalism. In 1915, at a time when Italy was about to join the Allied powers, he voted successfully for a scientific paper from Italy, which received a prize from the Prussian Academy of Sciences, where Planck was one of 4 permanent presidents. Planck also signed the infamous Manifesto of the 93 Intellectuals, a pamphlet of polemic war propaganda. But in 1915 Planck, after several meetings with Dutch physicist Lorentz, revoked parts of the manifesto. Then in 1916 he signed a declaration against German annexationism. Post-war and Weimar Republic. In the turbulent post-war years, Planck, now the highest authority of German physics, issued the slogan "Persevere and continue working" to his colleagues. In October 1920 he and Fritz Haber established the Nachgemeinschaft der Deutschen Wissenschaft, aimed at providing financial support for scientific research. A considerable portion of the monies the organization would distribute were raised abroad. Planck also held leading positions at Berlin University, the Prussian Academy of Sciences, the German Physical Society and the Kaiser Wilhelm Society. During this time economic conditions in Germany were such that he was hardly able to conduct research. During the interwar period, Planck became a member of the Deutsche Volkspartei, the party of Nobel Peace Prize laureate Gustav Stresemann, which aspired to liberal aims for domestic policy and rather revisionistic aims for international politics. Planck disagreed with the introduction of universal suffrage and later expressed the view that the Nazi dictatorship resulted from the ascent of the rule of the crowds. Quantum mechanics. At the end of the 1920s Bohr, Heisenberg and Pauli had worked out the Copenhagen interpretation of quantum mechanics, but it was rejected by Planck, and by Schrödinger, law, and Einstein as well. Planck expected that wave mechanics would soon render quantum theory his own child unnecessary. This was not to be the case, however. Further work only cemented quantum theory, even against his and Einstein's philosophical revulsions. Planck experienced the truth of his own earlier observation from his struggle with the older views in his younger years. A new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die, and a new generation grows up that is familiar with it. Nazi dictatorship and the Second World War. When the Nazis seized power in 1933, Planck was 74. He witnessed many Jewish friends and colleagues expelled from their positions and humiliated, and hundreds of scientists emigrated from Germany. Again he tried the persevere and continue working slogan and asked scientists who were considering immigration to remain in Germany. He hoped the crisis would abate soon and the political situation would improve. Otto Hahn asked Planck to gather well-known German professors in order to issue a public proclamation against the treatment of Jewish professors, but Planck replied, "If you are able to gather today 30 such gentlemen, then tomorrow 150 others will come and speak against it, because they are eager to take over the positions of the others." Under Planck's leadership, the Kaiser Wilhelm Society avoided open conflict with the Nazi regime, except concerning Fritz Haber. Planck tried to discuss the issue with Adolf Hitler but was unsuccessful. In the following year, 1934, Haber died in exile. 1 year later, Planck, having been the president of the KWG since 1930, organized in a somewhat provocative style an official commemorative meeting for Haber. He also succeeded in secretly enabling a number of Jewish scientists to continue working in institutes of the KWG for several years. In 1936, his term as president of the KWG ended, and the Nazi government pressured him to refrain from seeking another term. As the political climate in Germany gradually became more hostile, Johannes Stark, prominent exponent of Deutsche Physik, attacked Planck, Sommerfeld and Heisenberg for continuing to teach the theories of Einstein, calling them white Jews. The Hauptamtwissenschaft started an investigation of Planck's ancestry, claiming that he was 1/16 Jewish. However, Planck himself denied this. In 1938, Planck celebrated his 80th birthday. The DPG held a celebration, during which the Max Planck Medal was awarded to French physicist Louis de Broglie. At the end of 1938, the Prussian Academy lost its remaining independence and was taken over by Nazis. Planck protested by resigning his presidency. He continued to travel frequently, giving numerous public talks, such as his talk on religion and science, and 5 years later he was sufficiently fit to climb 3,000-meter peaks in the Alps. During the Second World War, the increasing number of Allied bombing missions against Berlin forced Planck and his wife to temporarily leave the city and live in the countryside. In 1942 he wrote, "In me an ardent desire has grown to persevere this crisis and live long enough to be able to witness the turning point, the beginning of a new rise." In February 1944 his home in Berlin was completely destroyed by an air raid, annihilating all his scientific records and correspondence. His rural retreat was threatened by the rapid advance of the Allied armies from both sides. After the end of the war he was brought to a relative in Gar-Paragraph-Tingen. Planck endured many personal tragedies after the age of 50. In 1909, his first wife died after 22 years of marriage, leaving him with 2 sons and twin daughters. Planck's older son, Karl, was killed in action in 1916. His daughter Margot died in childbirth in 1917 and another daughter, Emma, married her late sister's husband and then also died in childbirth in 1919. During World War II, Planck's house in Berlin was completely destroyed by bombs in 1944, and his younger son, Erwin, was arrested due to the attempted assassination of Hitler in the July 20 plot. Erwin consequently died at the hands of the Gestapo in 1945. His death destroyed much of Planck's will to live. By the end of the war Planck, his second wife, and his son by her moved to Gar-Paragraph-Tingen where he died on October 4, 1947. Religious views. Planck was very tolerant towards alternative views and religions. In a lecture in 1937 entitled Religion und Naturwissenschaft he suggested the importance of these symbols and rituals related directly with a believer's ability to worship God, but that one must be mindful that the symbols provide an imperfect illustration of divinity. He criticized atheism for being focused on the derision of such symbols, while at the same time warned of the overestimation of the importance of such symbols by believers. Max Planck said, as a man who has devoted his whole life to the most clear-headed science, to the study of matter, I can tell you as a result of my research about atoms this much: there is no matter as such. All matter originates and exists only by virtue of a force which brings the particle of an atom to vibration and holds this most minute solar system of the atom together. We must assume behind this force the existence of a conscious and intelligent mind. This mind is the matrix of all matter. In 1944, Planck regarded the scientist as a man of imagination and faith, faith interpreted as being similar to having a working hypothesis. For example, the causality principle isn't true or false, it is an act of faith. Thereby Planck may have indicated a view that points toward Imlocato's research program's process descriptions, where falsification is mostly tolerable, in faith of its future removal. He also said, both religion and science require a belief in God. For believers, God is in the beginning, and for physicists he is at the end of all considerations. To the former he is the foundation, to the latter, the crown of the edifice of every generalized worldview. On the other hand, Planck wrote, to believe means to recognize as a truth, and the knowledge of nature, continually advancing on incontestably safe tracks, has made it utterly impossible for a person possessing some training in natural science to recognize as founded on truth the many reports of extraordinary occurrences contradicting the laws of nature, of miracles which are still commonly regarded as essential supports and confirmations of religious doctrines, and which formerly used to be accepted as facts pure and simple, without doubt or criticism. The belief in miracles must retreat step by step before relentlessly and reliably progressing science, and we cannot doubt that sooner or later it must vanish completely. Later in life, Planck's views on God were that of a deist. For example, 6 months before his death a rumor started that Planck had converted to Catholicism, but when questioned what had brought him to make this step, he declared that, although he had always been deeply religious, he did not believe in a personal God, let alone a Christian God. Honors and awards. Paul Ammar Copyright Right for Science and Arts 1915, Nobel Prize in Physics 1918, Lawrence Medal 1927, Franklin Medal, Adlerschale Reichs, an award from the German Reich President, Max Planck Medal, Copley Medal. Planck received honorary doctorates from the universities of Frankfurt, Munich, Rostock, Berlin, Graz, Athens, Cambridge, London, and Glasgow. The asteroid 1069 was named Stella Planckia by the International Astronomical Union. Publications: Planck, M. Alberein Verbesserung der Wienschen Spektralgleichung. Behandlungen der deutschen Physikalischen Gesellschaft 2, 202 Euro 204 are translated into H.D. on an improvement of Wien's equation for the spectrum. The Old Quantum Theory. Pergamon Press PPA 79 Euro 81. LCCNA 66029628 Planck, M. zur Theorie des Gesetzes der Energieverteilung im Normalspektrum. Behandlungen der deutschen Physikalischen Gesellschaft 2, 237 are translated into H.D. on the theory of the energy distribution law of the normal spectrum. The Old Quantum Theory. Pergamon Press. PA 82. LCCNA 66029628 Planck, M. Entropy und Temperatur strahlender Wachcurrency RME, entropy and temperature of radiant heat. Annalen der Physik 306, 719 Euro 737. Bibcode, 1900 p. 306-719 doi, 10.1002/ANDP 19,003,060,410 Planck, M. über irreversible Strahlungsvorgänge currency NGE, on irreversible radiation processes. Annalen der Physik 306, 69 Euro 122. Bibcode, 1900 p. 306. 69 doi, 10.1002/ANDP 19,003,060,105 Planck, M. über das Gesetz der Energieverteilung im Normalspektrum. Annalen der Physik 309, 553 Euro 563. Bibcode, 1901 and p. 309 553 doi, 10.1002/ANDP 19,013,090,310 are translated in Ando, K. On the Law of Distribution of Energy in the Normal Spectrum. Retrieved October 13, 2011. Planck, M. Treatise on Thermodynamics. Og, A. London, Longmans, Green and Company. Ola 72466991 Emma, Planck, M. Volksungen 1/4 die Theorie der Wachcurrency Raumstrahlung. Leipzig, J. A. Barth. LCCNA 07004527 Planck, M. The Theory of Heat Radiation. Mazius, M. P. Blackiston's Son and Company. Ola 71546661 Emma, Planck, M. 8 Lectures on Theoretical Physics. Wills, A. P. Dover Publications. ISBN A0-486-69730-4 Planck, M. zur Geschichte der Erfindung des physikalischen Wirkungsquantums. Naturwissenschaften 31, 153 Euro 159. Bibcode, 1943 NW, 31153 doi, 10.1007/BF0147573 See also. References. Bibliography, Atchell, Amir D. Entanglement, Chapter 4. ISBN 978-0-452-28457-9, Heilbronn, J.L. The Dilemmas of an Upright Man, Max Planck and the Fortunes of German Science. Harvard University Press. ISBN A0-674-00439-6. Pickova, Clifford A. Archimedes to Hawking, Laws of Science and the Great Minds Behind Them, Oxford University Press, 2008, ISBN 978-0-19-533611-5. Medor, Jean, Pike, David. Hitler's Gift, The True Story of the Scientists Expelled by the Nazi Regime. New York, Arcade Publishing. ISBN A978-1-61145-709-4. Rosenthal Schneider, Ilse Reality and Scientific Truth, Discussions with Einstein, von Law, and Planck. ISBN 0-8143-1650-6. External links, works by Max Planck at Project Gutenberg, works by Max Planck at LibriVox, annotated bibliography for Max Planck from the Alsos Digital Library for Nuclear Issues, Max Planck Encyclopaedia Britannica article, Max Planck biography www.nobel-prize-winners.com, Max Planck. Institutes of Natural Science and Astrophysics, Cinematic Self-Portrait of Max Planck, Berlin Brandenburgische Akademie der Wissenschaften, 1942, Nobel biography, Live via work personality exhibition on the 50th anniversary of Planck's death, Max Planck, Planck's constant, and Schrödinger's cat.